проверите, да, что пошло красиво.
So is it true that the number of connected components of is n or?
No, it's no. This doesn't say anything because yeah. So for the simple reason, I mean, because first of all, some connected components can map trivially, can map to unit. Yeah? And the second is that we cannot say that this is surjective. So for any reason. So this, I mean, this, the only thing that you know, if you have this collection of characters and you know that G's permutes them, then they form one orbit. So this you know. But so this means that the image of G is sufficiently big, so at least if these characters are different and permuted, so this means that at least the G cannot map to a subgroup or symmetric subgroup of lower number of elements, because otherwise it will fix some other, just fix some subsets here. Yeah, so that's why. So the image will be sufficiently big here, but you cannot say much. And so for our purposes, there is no much reason. Yeah, so now let us do the small trick. So now you have the subspace. So now this W is the sum of this V chi I is G invariant subspace. Subspace of V. And and here you already have a vector, so here you have the corresponding component V chi 1, so you have a vector V here, and the H is HV is just chi of chi of H V, and H is characterized precisely by this property. So if you find the elements G, then GB will be a chi of HV. Then, of course, if it will be scalar, so then G belongs to H. So we have the corresponding characterizing property of our elements of H. So they are acting by the vectors on the scale. Notice that now consider the set of endomorphisms of V. So of all linear operators on V. Or just the group of linear transformations. So this our G acts on the group of linear transformations. So G acts on G on endomorphisms of V. Yeah? So acts on endomorphisms of V. Simply you have V, so endomorphism of V, and you map operator to A maps to G, A, G mix. So you have a natural, since G acts on W, so this allows you to act on the linear operators on W. So how character, notice that when it acts, so also the element of G permutes V chi. So if you look at how your matrix of G is written, yeah, so you are this means that G maps. This is like it looks like blockwise permutation matrix. Yeah? So the matrix H, if you put basis for V chi 1, V chi 2, etc., V chi n, then H would act by so the element of H on this space act by chi 1 of H blockwise block diagonal. So this will be just diagonal matrix. And G will transform the blocks. Yeah, so if you apply G, you look at this block and it is G is a blockwise matrix. Yeah? So from this point of view. So if you look at the corresponding basis, so V chi 1, V chi 2, etc., V chi n, so G will look like blockwise matrix, blockwise permutation matrix.
Non-diagonal, okay.
I mean blockwise permutation. Yeah, so, okay. So this notice that if you look at this action, yeah, so if you apply H, so you look at the image of H. So image of H in endomorphism of V is also very easy to describe. So H acts as diagonal matrix on our space. So if you are looking at GAG inverse, you are just these are just blockwise scalar matrix, so that they act trivial. So H. So if you have H inverse, so then H maps trivial. So you see that yeah. So consider so here in the set of endomorphisms, consider the set of yeah. So if you consider consider blockwise operators. Yeah. So consider in endomorphisms of V. Consider blockwise operators, so block matrices. And if you look at the corresponding homomorphism, so H on each B lambda act by just yeah, so yeah, so H on each V lambda act by this scalars, and just a second. Yeah, so what I want to yeah, so if you are thinking, so consider the set of the following. So the set of so here in the set of endomorphisms of W, consider the subset, the direct sum of endomorphisms. Yeah, so the endomorphisms of V lambda, V phi, etc. One, two, etc. Endomorphisms V chi m. So this direct sum. Yeah? What? So you just consider this direct sum of each V is just a vector subspace, and you can consider just this direct sum of this endomorphisms. Yeah? So what is the action of H? Yeah? So H acts diagonally. So H acts as a scalar. Scalar on each endomorphisms. On each V chi I. So the operator, so it commutes with the operator. So the action of the form H. So saying that the operator is from the set, meaning that H simply maps Vi, V chi I to V chi I, and this shows that when you apply H as the conjugation, then this will be simply H. Yeah?
Excuse me. This matrix which permutes like blocks is not in common with right?
Yes, yes. Just I have written this one.
So this was an action of arbitrary J.
Yeah, so this was an action of arbitrary. Yes, this was action of arbitrary. And now I want to understand what. Just.
A has nothing in common with group G itself. It's just some.
Yes, yes. A is just the element of this form. And you see when H, so since H acts by the scalar on each vector space, of course, it commutes with all matrices. So A acts trivial. H acts trivial on this operator. Ну, то есть, как бы, если вы возьмете матрицу отсюда и подействуете H, то тогда H ничего не сделает. Потому что она просто каждый элемент. Здесь, каждый вектор отсюда, справа, слева умножается. And what is G? Yeah, so G acts on. So G acts on this set of endomorphisms. Yeah, so that since G maps V chi I to V chi J, it maps the the endomorphisms of V chi I to V chi j. So G maps element of G of this form. It maps endomorphisms of V chi I to endomorphisms of V chi j. This is just for the following, so just V chi I maps to V chi j via the element of G, and then you are applying the element of, so you are applying A here, and this, yeah, so taking inverse, so G inverse, yeah, so if you apply like this, yeah, so if you apply G inverse, then A, then G, then you get the element of that, so G inverse AG. So it will be the element of endomorphisms. Yeah, so that's why you have to write it down like this. So you have to take G, yeah, so this, yeah, so gives you, yeah, so A gives you the element of this endomorphism. Yeah, so given the element here, you get the element. So given the element of A, so then we get G inverse AG, the element here.
So G inverse is not a map from endomorphisms to endomorphisms.
It is a map from endomorphisms of the whole space, endomorphisms of the whole space, of the direct sum. I mean, I'm working at, so I'm looking at this one as in the direct sum, and just the element of G itself. It is the element that maps W to W, but it has additional property that some chi I is mapped to some chi J.
То есть мы должны записать не G, а G.
Ну, G вообще, ну, правильно писать, что сигма от I, которая зависит от G.
Я имею в виду, вот, снизу слева. Можно писать совсем снизу?
Да.
Нет, слева. Вот тут.
Да.
Мы пишем, можно так? Ага, да, вот так.
Да.
То есть это вот.
Вот это выражение.
Отлично.
Yeah, so this G maps the V chi to this corresponding that we put the J sigma ij, so the permutation that depends on J, and this means that if you look at the element, this holds for arbitrary, so this is defined for arbitrary endomorphisms, but if A precisely, if we look at A as the subset here, which fixes endomorphisms and just as the component here, it maps to the corresponding operator, which is here in the endomorphisms of Xj. So this means that G preserves the structure. So this means that G maps this subset. So this action of G of G on endomorphisms of V maps this direct sum to itself. So the sum of endomorphisms of Vi to the sum of endomorphisms And the H is characterized, so notice that if so this means that we have mapped our group G to some GL, so some linear group, so the product actually of these linear groups. So the GL of the sum of the homomorphisms. So it is actually a huge group, yeah? So we have mapped the G to the group of linear transformations of these guys. And the H maps trivially. Yeah? So H maps to this is some tau of homomorphisms, and the tau of H is trivial. It is homomorphic. So H is in the kernel, but notice that if you have an element of G, that if G acts trivially, on this sum of endomorphisms. So this means two things. That first of all, this means that endomorphisms of, if you apply element of G, endomorphisms of Vg maps to the same endomorphisms with the same number. Otherwise, the action of is non-trivial, yeah, because you just map to the different subspace. So otherwise, it is not. Otherwise, G maps a vector, an operator, to different subspaces. And also, it acts if you look, if you are looking at fixed G, so G restriction to endomorphisms of this fixed Vkj, it acts trivially here, so acts trivially, and the meaning that you are writing G inverse, and it is equal to GA for any matrix. And this means that G is a scalar. So it commutes with all matrices, so G is a scalar matrix. Scalar matrix as the matrix acting on the corresponding Vg. So G acts as a scalar matrix. G is scalar matrix on all as a matrix on, it is a scalar matrix as a matrix in endomorphism of Vg and Vkj, so this means that it acts as a scalar, on Vk. So in particular, it acts on this on the fixed Vk from which we started. So G acts by the scalar Why? So that means that G belongs to H. Because H is precisely, H is the stabilizer of this given vector. In G. For the scale of the corresponding line. So we established that we have a homomorphism of G into this group of linear operators. Here the H maps trivially, and if G fixes all the vectors, so if it is fixes all the elements here, then if the element of G fixes all the elements here is a trivial operator, then it belongs to H.
And from this you say it follows that it's like a phi?
It's a fine because it is a homomorphism of algebraic group to
Because it's a kernel.
yeah, it is a kernel. Yeah. But I mean, but we wanted to say H is a kernel, but it was a fine. But this shows that it is image in this group, image under homomorphism. If you have image under homomorphism, so yeah, so maybe this should be stated as an exercise, but
So image is constructible.
yeah, so image. So if you have G1 and G2 and you have phi homomorphism, and which is also a morphism of algebraic varieties. Then image phi of G is phi of G1 is a closed subgroup. Yeah, so you did this exercise actually by saying that it is constructible. For constructible group, it is equal to its closure. So this is it about this. У нас в 2:20, да,
Mhm.
Да.
So this finishes the proof. So I want to say something about isotypical components and isotypic components. And yeah, so is it clear? Any questions?
Yeah.
Clear. So the trick is that via the structure, so since you know a priori that G permutes these factors, you can map it into this small subset in comparison with just the group of all transformations. And they are saying that since you know a priori that G maps each endomorphisms in some other endomorphism, possibly in this space, this tells you that if G fixes such operator of this form, then it maps component to itself where it is a scalar. And if it is a scalar, the characterizing property is that it belongs. Knowing that you have one vector which is stabilizer and G acts on it as a scalar, you know that G belongs to H. And so this means that G is equal to lambda V high, and this means that taking this particular vector, I do not claim that all vectors are good for this purpose, but you know that there is a so just yeah, so just So maybe it is time to speak about Lie algebras. So Lie algebra derivations, differentials, derivations, and Lie algebras. Notice that, maybe I should speak a little bit about motivation for manifolds, and then I will recover something about algebraic groups. Yeah? So, what are tangent vectors? So suppose we're in the situation not of algebraic varieties, and the M is a manifold. For manifolds, you have the corresponding tangent space. Tangent space. So this is considering curves are up to equivalence relation, that thinking of them that the curves are called equivalent if they are tangent to each other. So here we have to consider actually parameterized curves. Otherwise, with the corresponding integer parameter. And the thing is that the tangent vectors are just equivalence class of curves such that they have the same tangent vector in your point x, but they have the same tangent vectors checked on the affine chart. So the definition is independent of the affine chart, but checking that curves are tangent, you can do it on the affine chart. And also you introduce what plays, so why do we need tangent vectors? Because you can differentiate the function in the corresponding direction. Yes, so given just a point and a function, in this point you can differentiate in the neighborhood, in the neighborhood of this vector on this affine chart. And this gives you also a function. Yeah? So this gives you a function which is derivative in respect to this vector. And of course, so this, this vector sits in this point, precisely this is a tangent vector in the corresponding point. So if you have a field of tangent vectors, so field of tangent vectors, produce many derivations. Yes, so the derivation from the, now we are thinking of the function that this was considered in the neighborhood of point. Yeah, so you picked up this derivation in x. And now you can differentiate, when you take this derivation, you get on the number, yes, so you get some number. Then if it depends on points, so this gives you, given a vector field, then you have the function that is a global function. So this can be viewed, these derivations can be viewed as follows. So tangent fields saying about tangent fields elements of tangent bundle can be viewed as derivations. Yes, so can be viewed as derivations. As derivations that maps C infinity functions to C infinity functions. And so you know that the derivation is additive with respect to argument and the way Leibniz rule. Yes, so you know that d of f1 plus f2 is d of so v now belongs to the C infinity sections of the tangent bundle. So it gives you the derivation and you have d of v just d of constants is equal to 0 and as a property and d of v of the product you have the corresponding Leibniz. So you have so this Leibniz rule, and then you want to make this. So the most evident way to pass to algebraic. To algebraic stating of what is vector field. So this is just the element of the corresponding derivation of the algebra of functions. So that the field is just a derivation of the algebra of functions. That satisfy this collection of properties. So that so just what you can do is that just here you can also think of this as so here if you are looking at this algebra functions you can also consider local elements. So given a point x on a fine variety. So there is a derivation. So given x on x, so there is a local ring. So there is a maximal ideal of elements that vanish in this point. So functions just f the maximal ideal such that f of x vanish at the point, and also you can think of you can localize your ring, so you can consider the corresponding localization with respect to this ideal, meaning that you invert all the elements which are outside of this ideal. Yeah, so you allow fractions with all elements that are outside of elements. Yeah, so that these are the subset of f divided by g, where g of 0, g of x is not equal to 0. So you allow denominators that do not vanish in the form. So this function has a good value, so it is denoted usually by OFXX. So these are functions that the largest subset of rational functions that have, so the rational functions are the functions of the form f divided by g unconditionally. And this is the largest subset where you can evaluate in the point x. So you see that this particular derivation for a fixed vector can be viewed as just d of v. If you fix this vector field, can be viewed as a map of x, so the function. So you need to consider function only in the neighborhood of x, and this is the just the motivation for that you have local ring here. And you have this derivation maps the function with values in the neighborhood of x to the functions with to these functions. Or
means that those are rational functions.
what?
Beautiful O is a rational function.
Beautiful O is the functions. So this are precisely this one. Localized KFX. So thinking of in the naive terms of topology, so these are the functions that can be defined in sufficiently small neighborhood. And thinking of them as the fractions, of course such fractions are defined outside of the set where G has poles. And it is precisely, since the g of x is not equal to 0, so this is often an open set.
So
A neighborhood.
again, idea is that this like OXX is same as tangent space because it's kind of identifying neighborhood with.
And OXX is not a tangent space, but you can recover tangent space. I mean for the line, so let us do the example. So for the line, you should consider the following. So you start with k of x, and you invert all elements. So if you localize by mx, you are allowed to write down f of x, polynomial in one variable, modulo g of x, where g of x is not equal to 0. Yes, so this has no zero constant term.
What is mx?
Maximal ideal of functions vanishing.
X, here x is a point,
X is a point.
and there x is a letter.
Yeah. Yes. And x is 0. 0 point on the final line. And here it is quite huge ring. I mean, now I want to recall what is tangent space. So the tangent. So here you were able to take the function and associate a value. So in the end of the day, you are associating the value of the corresponding field. Yes. So to the function, you in the point x, you are associating its derivative. Yeah?
But I'm dividing by delta t.
Нет, ну просто я написал производную по направлению.
There is no limit sign, I mean. Is it?
Yes, there is a limit sign, delta t tends to 0.
Okay.
I thought, I mean, since just x is a point in a fun chart,
I thought it was polynomial division like that. It should be like
actually, it is. I mean, for it's you are not far from it because if so, from the viewpoint of Taylor series, it is just divide. So you have this difference is divisible by delta t, and then you take it modular. So modular higher powers of delta. So this is just so this can be written as, of course, f of x plus v delta t minus f of x divided by delta t. If f is polynomial, then you just take it modular delta t, and you are getting an r. But delta t, so this just okay. So and this so having if you have a global derivation, so it would be the derivation of k of x to k of x, then of course then it is easy to extend it to fractions. And this is done via our usual rule. Just so you have this
So the idea is like we want to define not only global but local.
yeah, so so you want to define you want so we want to define global objects, and then you can extend if you have the derivation on the ring of functions, then you can extend it to the ring of fractions, and this gives you that this so this gives you that and also this defines I mean the same rule, because you are having denominator in the square and it is not equal to 0, then you get that this also extends the derivation to the local rings as so this means that you can if you have derivation, you can always extend it to either the local ring of a point, to localization, or to the fractions, to all fractions of your thing. And then I want to understand what is this map from the viewpoint of derivation. And now we assume that, so since we are looking at the field, so K itself sits in O of x as the functions, as constant functions. And this allows you to do the following. So this allows you to take the function f, And just to say that, yeah, so this, what I wanted to say, that the map that satisfies Leibniz rule and the maps of XX to K, so if V satisfies Leibniz, star, is equivalent to saying, star was arrested as Leibniz rule, so linearity plus Leibniz rule.
How such function can satisfy Leibniz rule if its function to K, function to K, to base field, can satisfy Leibniz.
If yeah, so if this, yeah, so Leibniz rule it is a little bit here. Of course, you are right, but this is written as follows. So it is f1 of x evaluated as in this given point. So d of f1 plus f2 of x d of 1. So which are numbers here? Yeah. So this means that d of Vx. Yeah. So this corresponding vector, and so this is equivalent. So this can be obtained by two things. So you can start with you can start by considering the following construction. You can start with global vector field from K of x to K of x, then extend it to O of x, x, and then you can just do the following. So take function, consider the map that is written here. So d now of maps from O of x, x to O of x, x. And here you can do the following. So here you can consider the other thing, that it is O of x considering of composition of this thing and reducing it modulo its maximal ideal. And if your if your field is algebraically closed, then this is K. Yeah, so when K is equal to K1. So you have this kind of differential, this kind of composition. And I claim that, or you can speak about this composition satisfying Leibniz rule. So you can do the following. So you can consider such maps that comes from D that satisfies Leibniz rule, and say that such T's, so such map T's, are in bijection with linear maps, of maximal ideal, modulo maximal ideal square. So maximal, the linear maps from this guy to here. Notice that this, what I'm writing down here, has a natural structure.
Извините, уже
Все закончилось? Ну, давайте я тогда вот буквально это договорю, и мы закончим. Yeah, so, и на следующий, ну, давайте я скажу, как это отображение построить. So, these maps are in bijection with these maps, and they are done as follows. So you can take a function of f of x. Yeah, so given the element from here, so it is a linear function L that maps m of x squared to t. And so I claim that you have to do the following. So take f, change it for f minus f of 0. It becomes the function of m of x. So it becomes a function on m of x. And then you just reduce it modulo m square and apply linear function. Modulo mx square. And so the claim is that, just notice that, so the claim is that this derivation b, so you can apply either to f and take modulo, so you can take, so saying that you are evaluating at 0, so saying that you can take df and take 0 value, value at x of this function is equivalent to say that you take d of f and take it modulo m x, and so what is has to be shown here that of course noticed here that if you just subtract a constant function, it will be again the same thing due to the fact that on constants the derivation is 0, and also you have to know that this is independent of just representative of modulo m square, but notice that so independent modulo m square mx square, since if you apply d of m square, it will sit in m square. So it is via Leibniz. So via Leibniz. So this is all for today. So next class I plan to speak about special case of the vector fields. So on this will be this will allow to identify the V algebra with the left invariant vector fields. And we shall discuss how to reconstruct the group out of so what are relations between group and its range.
Можете, пожалуйста, по-русски описать множество, которое вот such D.
Это по-русски скажите. Где?
Вот, которое such D, вот, по XX.
Вот это?
Да, нет, вот да. Вот то множество, которое справа, оно чисто invariant.
Ну вот это то, что пришло отсюда. То есть вы взяли D, которое пришло из дифференцирования на Algebraic Groups. Которое...
Ну вот, вы просто вначале рассказывали по там касательной пространству, что касательный вектор это локальное дифференцирование, то есть это по сути
касательный вектор это локальное дифференцирование.
которое тоже
Касательное векторное поле это уже глобальное
да,
дифференцирование.
ну вот, это аналог касательного вектора к...
Да, но вот это аналог касательного векторного поля, а вот это буквально, да, аналог касательного. Но это и есть касательный вектор к субу, это можно также
касательный вектор, ну, это вот мы рассматриваем идеал определенного фактора.
Да.
И вот это касательный к самому x. Или что то же самое касательный к...
Ну, к кривой какой-то.
Ладно, что-то вращите.
Нет, ну просто надо помнить, что мы касательные вектора играют роль просто, говорить о касательных векторах равносильно тому, что вот говорит о дифференциации.
Нет, вот OXX это...
А OXX это, кольцо функции, которое с ростков функций, которые рассужают это.
Это типа функции из окрестности.
Функции такие, что можно перейти к какой-то маленькой окрестности, где они будут определены. То есть это функции без фиксированных, это называется ростки функции, то есть они функции без фиксированной области определения. Мы складываем, у одной функции может быть одна область определения, у другой другая, мы складываем.
Понятные кривые, те, которые есть хоть какая-то... нет. У них кривые, например, неверно. Понятные кривые, это если какая-то где они совпадают.
Ну это правда.
Нет.
Ну в смысле,
которые
нет, не совпадают, но они там касаться должны. Если грубо говоря, что вам вся кривая не нужна, а вам нужна эта окрестность.
Нам нужен только вектор скорости. Но вектор скорости не равно поведению в окрестности. Вот в этом
конечно, могут быть разные, иначе бы там.
Что вот это там
кривая.
Ростки, это же, что есть окрестность.
Это класс эквивалентности, ростки, но там это класс эквивалентности. Да, там именно это параметризованное.
Ладно, видимо, это плохая аналогия.
Что?
Это тогда плохая аналогия.
В смысле, вы должны думать о кривых, у которых фиксирован параметр.
Ну, все равно, вот у них есть вектор скорости как бы кривых, и кривые с совпадающим вектором скорости, это не то же самое, что ростки будут.
Функции? Нет, они вообще не связаны никак.
Сказать, что не эквивалент в том смысле, что не направление.
Но что же касательное пространства, где не ростки?
Касательное пространство.
Касательное пространство это не раз. Просто кривые вам не нужно.
Это дифференцирование ростков. Такая идея.
Да.
Ага.
Ростков функций.
Дифференцирование ростков функций, касательное пространство точки. Это верно.
Да, но вы просто любой вектор, грубо говоря, вы обычно представляете в виде аита, d по dx, аита, сумма, да, можно говорить о вот этом, где вот это элементарный базис, но можно говорить про дифференцирование по направлению сразу, не переходя ни к какому базису. Вот этот локальный базис, но идея в том, что локальный базис для определения вам нигде не нужен.
От меня просто устраивает лозунг касательно пространства дифференцирования ростков.
В алгебраическом мире, да.
А не в алгебраическом качестве только.
Там тоже, и там те же ростки, просто в алгебраическом мире функция восстанавливается по своему ростку, а в топологическом
Дифференцирование все равно в точке.
но все равно вы интересуетесь